Hi, in this video we solve question number 23 of IIT JAM 2021. Here's the question. We are given a domain D, which is the R2 plane minus the x-axis, and we have a function defined as f of xy equal to x times sine 1 by y. Now in this function, one thing to notice is that it is a composition of continuous functions on the given domain. For example, x is a continuous function, sine is a continuous function, and reciprocal of y is a continuous function whenever y is non-zero. So on the given domain, f is a continuous function because it is a composition of continuous functions. So option A is wrong. Now in the given function's definition, one thing to look for is this function sine 1 by y, and it is known that this function oscillates near 0. For example, let us consider two sequences. These sequences will reveal this nature of sine 1 by y. Now, suppose we have this sequence yn equal to 1 over 2 pi n and zn equal to 1 over 2 pi n plus pi by 2 for all natural numbers n. Now, it is easy to see that these sequences converge to 0 as you take n tending to infinity. So we have y tending to 0 and z tending to 0 as n tends to infinity. But if we compute sine function at 1 over yn, what we get is this is equal to sine reciprocal of yn is 2n pi, which is equal to 0. And similarly, sine 1 over zn is sine 2n pi plus pi by 2, which evaluates to sine pi by 2, which is equal to 1. Here's a graphical representation of the function sine 1 over y. This is how it looks like. Now, as you are away from 0, it behaves like a wave. And as you start going near 0, the waves start getting cramped into each other and it oscillates vigorously near 0. So you don't really have a limit as y tends to 0, as these sequences reveal. Now, if you take any x real number, then we have the following. F evaluated at xyn is equal to x times sine 1 over yn, and we know that this is equal to 0. Similarly, f evaluated at xzn is equal to x times sine 1 over zn, which evaluates to x times 1 equal to x. So from these two evaluations of the function, we see that if x is non-zero, then we have the limit of these sequences f(x)yn is equal to 0 that we know. If it is not equal to x, then this we know x is equal to limit of this sequence f(x)zn. Of course, these limits are for n tending to infinity and tending to infinity. So what we have shown is that these two limits are not matching, even though xyn and xzn both converge to this limit x0. So this reveals that f is not continuous at x comma 0 whenever x is non-zero. Alright, now, but what happens when x is equal to 0? It turns out that f can be extended continuously at the origin, that is point 0 comma 0 to origin. Let's see an argument for this. Okay, what we have is this. 0 is less than or equal to modulus of f(xy) for any xy. This is equal to modulus of x times modulus of sine 1 over y, and we know that modulus of sine is less than or equal to 1, so this quantity is less than or equal to modulus of x. So in this case, what we do is this. Let us define the function at 0, 0 to be equal to 0. Now, if we do that, then we have something like this. 0 is less than or equal to modulus fxy minus f00, which is 0 by definition. So this we have already evaluated it to be less than or equal to modulus of x, and modulus of x is less than or equal to the square root of x square plus y square. Now this is nothing but the distance of the point xy from the origin. By definition, Euclidean norm it is. So what we have proved is the following. By definition, we have proved that limit of point xy tending to 0, f of xy is equal to 0, which by definition is f of 0, and hence the function, extended function, is continuous at 0, 0. Now let us look at the option. Option B says that f is a continuous function on D and cannot be extended continuously to any point outside D, which is wrong because we know that can be extended to 0, 0 continuously. This automatically makes option C the correct option because f we know is continuous on D and can be extended continuously to origin as well. So option D must be wrong, which can also be verified.